Okay, welcome back. This experiment 6 will complete later because it's a schematic, so we have to use the LT spice. So let me complete with the first model sim. So let's go to this experiment 7 and 8. So here we have this experiment 7, D flip-flop. Okay. So D flip-flop theory, nothing much. You all know about that. So it is just having let's say this is the black box. So it has got D input and it has got Q output. And then there is a clock. There is a clock associated with this. And there is a reset pin. Okay. So in classroom, in the lab session, we have discussed. So there are several types like, you know, this your clock can be positive edge clock or it can be negative edge clock. So this is a positive edge clock or it can be a negative edge clock. So this one we have seen. And then this reset also can be of two types. Active high reset, active low reset. So this is active high reset and there is a active low reset. So this also we have seen. And in the classroom, we also have seen synchronous and asynchronous reset. So you have got this synchronous reset and asynchronous reset. So you have got this asynchronous reset. So you have to understand all of these differences. Okay. So here, this is how we are representing when this is in line with this clock. This reset is in line with this clock signal here. The way it is shown, it is a synchronous reset. If I am representing, let's say like this is your D input and you have Q output. I'm representing clock is this one, but I'm representing reset here. Then that is the asynchronous reset. So this reset is the asynchronous reset. Here it is a synchronous reset. So you have to remember this. And in case of active high reset, active low reset, how we represent, let's say it is synchronous active high reset. So you have got D here and this is your Q. So synchronous active high means this is active high, what we have shown here. This is active high. For active low, you will put a bubble like this, then you represent your reset. So that says it is a active low reset. Active low means whenever this reset is low, at that time your output is it is brought to some known state. Generally, it will be 0. So, and in case of positive edge clock, this what we have shown here, it is a positive edge clock. But in case of negative, negative edge, then we have to represent here this way. We put a bubble here. This way we put, and then we connect this clock here. So that means that is a negative edge clock. So all of these things we have discussed. So now, how do we model this one? So understand this fact also. To model this, synchronous reset, to model synchronous reset. So we have In Verilog HDL, we have to write like this always at the rate pause edge clock. Pause edge your clock variable name. It may be CLO, CK, or CLK like that. So, so here, this always is a keyword. This always is a keyword that is a procedural block or procedural construct. This is a procedural block or a construct, procedural construct, procedural block or procedural construct. And this at the rate is a event control operator. At the rate is a event control operator. At the rate is the event control operator. And this posage is a keyword. It is lowercase. This is a keyword, posage. And there is another keyword called negedge. Negedge. Okay, posage and negedge. These are the keywords. So in case if it is a if it is this one positive edge clock, then you have to use this keyword. If it is been asked to write a negative edge D flip-flop, then you will be using this negedge keyword. Then in case of synchronous reset, here after this always at the rate pause edge clock, you will be writing if reset. If reset, if you are writing, it means what? If reset equal to equal. This is equivalence checking operator, not assignment operator. Double equal means you are checking whether this reset is equal to 1 or so equivalence check operator, not assignment operator. So simply writing if reset means that is equal to this statement. So it means what? This is active high reset. So we have discussed here active high and active low. Two types of resets are there. So then synchronous reset means that is what here. It will not be there in sensitivity list. This area is called this complete after this at the rate. That is after event control operator, you open a parenthesis. Inside parenthesis, whatever the variables that you are going to put here, this area is called sensitivity list. Sensitivity list. In sensitivity list, now currently we have only positive clock. So it means what? Whenever this positive edge occurring, then that block will be triggered. This always block will be triggered. Whenever positive edge occurs, then only this block will be triggered. This block means under always whatever the statements are there, they will be executed. So it means what? If reset is high or not is checked with reference to the clock. So that's why this type of writing, is called synchronous reset. Whereas in asynchronous reset, what happens is asynchronous, what happens is always at the rate, we have to write here posage clock, comma, the same line here. Yeah. Here, just a minute. Comma. Here you write posage reset. So this way, if you are writing, what happens is it is like irrespective of your this posage might have occurred or not occurred. The moment when this reset occurs, that is high, reset is high. So whenever reset is going from low to high, so this is the transition occurring. So then this block will be triggered. So sensitivity list, this is sensitive. This block, always block, is sensitive to the listed variables here. So earlier we have listed only this here, only clock. So when pause edge is occurring, then only this block is triggered and whatever the following statements are there, they will be executed. But now what happens here is pause edge clock and pause edge reset, both are there. Na? If reset is not, clock is, pause edge is though not occurring, but the moment when pause edge reset occurred, so this block will be triggered and whatever statements are there, they will be executed. Since it is not with reset is not working with reference to the clock, this kind of reset is called asynchronous reset. So making sense, pause this video, little bit, go back here, what I spoke here with reference to this synchronous reset, and then come to here, you will understand. Listen once or twice or thrice. Okay. So, but you must have clarity. If you are not having clarity on this, you please ask me uh, in the comment section or make a phone call. I will respond. So, with that understanding, now let us go to the coding of this flip-flop. So, we'll be coding for positive edge clock and synchronous reset. Okay. So let's do that. So double click this one. Then just a minute. I just wanted to bring this one to the other side here. So here, if you click on jump start, then create a project, go to create a project. Here, you just give the project name. This is D flip-flop, DFF, and ensure that this project location, you are not working here in the C drive, Intel FPGA. So this is the path where actually we have installed our software. You should not be working here. So go to browse. On my desktop, I have created here. I'll show that. On my desktop, I have kept this lab demos folder. I'm just going inside that folder. Even inside that folder also, I'm going to create one more folder with my project name. So that is DFF. Now select this folder, that is DFF, and remaining two keep as it is. Click OK. So now create new file here. So that is one is DFF and this you have to change. Add file as type. This you have to change to Verilog. Okay. Then click OK. Then add one more file, that is test bench file TB underscore FF. That is DFF, D flip-flop. And then change this file type to again Verilog. Okay. Don't make mistake here. Click OK. Now close this. So double click this DFF and double click this tb.v. So now you can see the tabs here. So here, DFF tab, this one, and this is test bench tab. So let's go start coding first D flip-flop. So module, this is your module, DFF, and this one has got primary inputs are this one. One is your D input itself, and this is clock, and this reset, and then output Q. So you have three primary inputs and one primary output. So with that, D, comma, clock, comma, reset, comma, Q. Now the type declaration. Input D, comma, clock, comma, reset. And output is Q, semicolon. Don't forget putting the semicolon at the end of the statement. Then always at the rate pause edge clock CLK. The variable we are using is the CLK for clock. Now, if multiple statements are there, you have to have begin and end. Inside this begin and end, if reset, that is the active high reset, then what we want to do is we assign Q with the 0. There are two types of operators. One operator is blocking operator, the other is non-blocking operator. So this is called blocking assignment operator. And if we use less than or equal to, this is called non-blocking assignment operator. So in sequential circuits, we have to use non-blocking. This is blocking, and this is non-blocking. So we have to use non-blocking assignment operator. This is non-blocking assignment operator. Else, Q will get the assignment of D. Whatever there on the D, that is what Q is going to get. So begin end is over. After that, we have to put an end module. That is the enclosure for that module. Module and module. So we have done with our D flip-flop. Now click on save. Now we have to generate the test bench for that. To generate the test bench, what is required is, so we have to generate one clock. This is one input. And we have to generate our reset signal also. So we cannot keep reset for longer time high, because if you keep for longer time high, then always you will have on Q output 0. So for a while, this is high. After, once you remove your reset, you have to start with your D. So D, let us say initially whatever it may be 1 or 0, which is unknown to us. So unknown is represented as X. Now here you are applying 1. Here applying 1. Okay. So next clock edge, here at this clock edge, I am applying less than 0. So one more clock edge, let's take. At this clock edge, I am applying 1 again. So that's what my D is. This is my D. Let's say this is my reset. This is my clock. So these are the things that I have to generate in my test bench. So once you apply these values to your DUT design under test, that is your D flip-flop, then we have to expect output according to the D flip-flop nature. So what is the D flip-flop nature that we have written down? Whenever there is a positive edge clock, whenever your reset is high, there where your Q is 0. That's what we have defined. Previously unknown it is, whatever it is. But here it is 0. Next, whenever there is a clock, but there's no reset, then whatever D is there, that D is seen on the output. So this is 1. So that is what we see 1. Now at this clock edge, your D is 0. So we also see the 0. At this clock edge, your D is 1. So we also see the 1 in the output. So that is what we are expecting on the output. So see that we are generating clock reset D in the test bench. So let's go to the test bench here. Now here, backport, time scale, 1ns/1ps, module, 1ns, that is the module name, TB test bench underscore DFF, and then here our module will have it. So here, just go to your design file and copy these things. Copy them and paste it here. Now this one will come after your input and output. After your input and output here. And after DFF, we have to give some space and give DUT, that is design under test. That is instantiation name. DUT stands for design under test. You can give, by the way, any name. So this is called what it is called? It is called instantiation name. Okay. Now, as said in test bench, input will be changing to reg. Output will be changing to y. Okay. Now here, after that, initial. Here I am going to have multiple statements, so begin and end is required. In this initial, if I want to display on the console, I have to have the dollar monitor and then open the parenthesis, close the parenthesis, end with a semicolon. Inside the parenthesis, double quote. What is that you wanted to display? At the rate time, percentage G, that is for time. NS is to print on the console for nanoseconds. And then I wanted to print my D value in binary. And then I wanted to print my clock value in binary. And then I wanted to print my reset in binary. Percentage B is a format specifier for binary. Q also I wanted to print in binary. So now you just copy this, all these variables here after double quotes, comma. For this percentage G, what is the reference? That is dollar time. System function is the reference for that percentage G. For remaining, this percentage B, these are the references like D, CLK, reset, and Q. After that, I am initializing my clock to 0. And I am also initializing my reset to 0. So that's what I am doing in this initial block. And then I have to generate my clock. So to generate clock, always, this statement always, what it does is over a simulation period, it will keep executing. Let's say you are running simulation starting from 0 and going till 500 nanoseconds, let's say. So if you are giving delay of hash 5 for always and giving some signal like this clock, and this is the negation operator, and then you must have already initialized this clock, which we did in the initial block with a 0. Now what happens? For every 5 from here, starting from 0, 5. From this 5 to another 5. This 5 to next 5. So for every 5, this will be like toggling. Because of this negation operator, it will be toggling. 0, 1, then 0, then 1, then 0, like that. So this is becoming the clock. So we are generating clock like that. Now here hash, that is hash point CLK equal to negation of CL. Negation of CLK and then some. Next, what is that we have to do is we have to apply our D and reset, right? For that, one more initial, begin, and end. Here, I know my clock is going to happen positive edge at a 5. So what I will do is just before that, at hash 3, I make my reset high and I will wait till the positive occurs, till the positive clock occurs. So what happens here is, according to this code, we are going to have this scenario positive clock and then reset high. Then we will see this, phenomenon, that is Q being assigned with a 0. After that, I will just wait one time unit and then I will be removing my reset 0. Reset means, you know, this 1 I am removing and keeping 0. So when I'm doing that, I'm also doing this D value, I'm applying 1, and then I will wait for this clock to occur. So here I'll wait this clock to occur. Now what happens is, according to the code, I have set this reset 0. I have kept D ready. When this pause edge occurs, it will not go here if reset high, there's no reset high. So it will not be going to this line number 10. It will come to this one. D I already kept 1. So that one being applied to this key. So that is what happening here. So one more scenario also I wanted to test. That scenario is uh, D uh, D0. So for that, again, I will just wait for one time interval. And then reset, I already have made this 0. Again, I don't need to make 0. I simply make my D value to 0. And then I will wait for the pause edge clock. I will wait for the pause edge. So again, the same explanation. So here pause edge clock is occurring. There's no reset. Your D already have set to 0. So that 0 will be assigned to the Q here. So once this is done, if you want to check few more such scenarios by giving 1, 0, you can check. So like again, #1, just wait for #1, some delay, and then apply your D to 1, and then wait for the positive stroke. Positive. So after that, you can stop your simulation. So after that, anytime you can stop your simulation. So I'll just wait for #1 and then stop. $stop and then semicolon. So this initial begin is here, and then this module needs to be enclosed with this and so this is ready now. Save this file. Now compile. So but before compiling here, one change you required to do. This queue is getting assignment within this procedural construct. So what is always, I already told, always is the procedural block or construct. So within procedural block or within this procedural construct, left hand side, if you are assigning something, that left hand side variable must be belonging to variable data type in that reg here. In this case, reg it is. So there are total 5 variable data types are there. Variable data types. So one is in that first one is let's say reg. The second one is integer. The third one is real. The fourth one is you have time. The fifth one is real time. So we use real time, time, and this real in simulation. But for design purpose, we use this reg and integer. So since this is the design, so we're supposed to be using the reg here. Integer is used for loop index values. Okay. So save this one. Now see that there's no asterisk on either of these files here. That ensures that we have saved our files. Then go to compile, compile all. Wait for here the status. So this is successful and this is also successful. Now go to simulate, start simulation. Locate your work folder, expand this plus sign just beside work, left hand side. Get this plus. Then select your test bench module name, click OK. So once you do that, now ensure that here the SIM tab is there here. So once SIM tab comes, then you can see here this, SIM default here. You can right click and you can add wave. So if you do, all of the signals will be added to waveform window. Now here also I said in my past videos, change the speed to N in nanoseconds. Now click run. So now you can see in the waveform the results here. To see complete view, click here and click on the zoom full. So you will have complete view of this. And here your console results. So you have to develop this justification. You have to develop these skills. How do you justify your results? So put them in order. First I'm dragging this clock above here and then reset here, ordering here, just ordering them, and then DQ, that is fine. So when clock is high here and your reset is high, so you can see our Q is 0. When next positive edge clock occurs, next positive edge clock occurs here, positive edge clock, their reset is 0. So whatever the D value is there, that will appear on the Q. Same thing happening here. The D is 1, so our Q value is 1. This is ST is status 1. So now on the next positive edge clock. So to go exactly to the positive edge clock without you dragging here, here are the helping things. Toolbar. So here if you place find previous falling edge, here find next falling edge, here find previous rising edge. So here next rising edge. So like that, this is for transition. We want to go from this transition to this transition. You can use this one, but at that time you must have selected this signal. Then it will work. So then it will is going straight here. Instead you dragging this one. So pause here, pay attention what I said, and do it on your own once. Here you have the positive edge. Your set is not there. You have the D value 0. And this 0 is what's seen on the cube. So like that, you have to justify your output results also in external paper. Okay. If you have any doubts, please put them in comment section or make a phone call. Okay. Then how to stop this simulation? Go to simulate. Click on this end simulation. So that way you stop your simulation. Okay. So that completes our uh, this experiment 7. So I left with doing 2 more. I'll do it. Okay, then thank you.